Right then, so I had to stop because I was afraid if I kept going up before I was going to just be wasting my time. So I'm going to have to do this in part two. Let's go ahead and keep going here. I'm not sure what causes that little glitch, but that's the second time it's happened. So if I can figure out what's causing it, then I'll obviously make it stop. So what data would you need to estimate the money you'd need to drive from New York to LA? So you would have to know how far it is and how many miles a gallon you get, so you can see how many gallons of gas you'd have. And then you'd also have to know the price. Uh, so basically, what you would need would be an average price per gallon. So you need to know three things. You'd need to know the distance, the price per gallon on average, and also how many miles a gallon your car gets. So you multiply or divide actually the number of miles by the number of miles per gallon. You can multiply it if you use dimensional analysis, so it's either way, times the price per gallon. So the way that you would do this, if you want to end up with dollars here, which is what you do, you want to wind up multiplying the dollars in the numerator. So let's see, to start off with, if you start with the miles, let's say it's 3,000 miles, then you want to multiply that by gallons per mile. So, I mean, I know that sounds like it's opposite, and it is, because usually we would say like 20 miles to the gallon, right? But you just flip it upside down. 1 gallon to 20 miles. So 3,000 miles, let's just say times 1 gallon per 20 miles. So that's one conversion factor. And then let's say the number of dollars, but let's just say $2 per gallon. And the gallons cancel, the miles cancel, and you're left with dollars, which we'll see that. So if you didn't get all that, you'll see it on the next slide or whatever. That's called dimensional analysis. So let's go ahead and go to the next slide. Okay, so here I actually assumed 25 miles per gallon. So I'm optimistic here. My truck that I drive doesn't get that. I mean, it anyway. And I assumed cost of gas was 220, which is what it was when I made this slide up, I think. Anyway, so you would multiply, and then it's 3,200 miles instead of 3,000 here. All right, so anyway, multiply the 3,200 miles times the number of gallons per mile, which you don't have to stop and figure out how many gallons per mile. Just write down 1 gallon over 25 miles. That's the same thing as 25 miles per gallon, right? It's just that you're flipping it upside down. Remember, I told you that you can do that because in your case, for your car, 25 miles is equivalent to 1 gallon of gas. So it's just like you're multiplying here. You're starting with 3,200 miles here, and you're multiplying by 1 here, and then you're multiplying again by 1 here. So you're going to wind up with the same thing you started with. It's just that you're converting it to a different form. So, I mean, you're converting 3,200 miles in your car at the rates of gasoline at the time you drove to the number of dollars you spent. Okay, so anyway, when you multiply all this out, the miles cancel, the gallons cancel, and you wind up with dollars only, and it's $282 approximately. Next slide. Okay, let's go to temperature. Next slide. So temperature, there's mainly the Fahrenheit, which they don't use that much in science, if at all. So usually you'll use either Celsius, which is also called centigrade. These are synonymous. And Kelvin. The only difference between 2 and 3 here is that Kelvin, you would add 273, as I said before. So 20 degrees Celsius would be 293 Kelvin. So to go from Celsius to Kelvin, you would just add 273, which I'm not going to, I would just write that out real quick if I were like teaching in a classroom, but it takes forever to do that with this little thing here. So I'll do it this once, but just to explain to you why I won't be writing a lot here. So plus 273 gives you your Kelvin. 25 degrees Celsius or centigrade would be 298 Kelvin. So going back and forth here, if you want to go from Kelvin to Celsius, you just subtract 273. So 298 Kelvin would be 25 Celsius. To go from Fahrenheit to Celsius or back, it's a little more complicated, but it's not hard. You just, if you want to go, for example, from Celsius, let's say you've got 20 degrees Celsius, the formula is that you first multiply by 9 over 5, which that would be 36 if you did that, and then add 32. So if you wanted to go from 20 degrees centigrade to Fahrenheit, you would go 9 over 5 times 20 would be 36, and then you add 32, so that's 68 Fahrenheit. 68 Fahrenheit. And then in the reverse direction, you would go, okay, if I want to go from Fahrenheit to centigrade, I go 68 minus 32 would put me at 36, and then multiply that by 5 over 9, not 9 over 5, 5 over 9, and that would be 20. So that would take you right back where you started from. Let's go to the next slide. So I'll let you pause this and look at it if you want to. Let's go to the next slide. So here are the formulas. If you want to convert from centigrade to Kelvin, you just add 273 and vice versa. And then here's your formula. If you want to go from Fahrenheit to centigrade, you first subtract here. So you have to remember the order here because the order is important. So to go from Fahrenheit to centigrade, you first subtract the 32 and then multiply by 5 over 9. To go from centigrade to Fahrenheit, you multiply first and then add 32. And I'm not going to spend a lot of time on this. If you aren't familiar with this already, just pause the video right here and just look at these. And you might do some practice. Just, try, I don't know, try 40 or something like that, or 45 degrees centigrade and convert it to Fahrenheit and just see what you get. Next slide. At what temperature does degrees centigrade equal degrees Fahrenheit? And one of the little unique features of when I'm doing these is these presentations do not allow you to go backwards. So what I have to do is I have to get everything said before I go to the next slide, or else I'm stuck. So I can't go back to the slide that we just looked at, but the formula was like degrees Fahrenheit would be the degrees centigrade times 9 over 5 plus 32. So if you want to get the temperature, and there's only one where degrees centigrade and degrees Fahrenheit are the same, you just assume, okay, if we don't know what it is, so let's just call it X. So we're going to be doing that a lot in this semester. So just call it X. And so it's going to be X for both, right? The degrees centigrade is going to be X, and the degrees Fahrenheit are going to be X. So just say, instead of degrees centigrade, put X, and instead of degrees Fahrenheit, put X. So what you wind up with is X, which actually I'll just say it and then I'll show you on the next slide. Okay, so X equals 9/5 times X plus 32. Let's just go to the next slide. So you just put X here for the degrees centigrade, and then here also for the degrees Fahrenheit, and that T stands for temperature. So TC is temperature centigrade, TF is temperature Fahrenheit, and then just solve for X. Okay, just substitute in X for both of them and solve for X, and I'll tell you what you're going to get. And I recommend you memorize this number just so that if you get this on a multiple choice, you can just write it down and you don't have to do all of this. It's minus 40. If you don't believe me, just try it. So substitute in minus 40 here, and then see what you get when you do all of this stuff on this side of the equation. You should get minus 40 over here too, and you will. If you don't, you did something wrong. So I'll just give you a hint. So just memorize that if they ask you this, which they could, I think one time they did ask that on the final, then just your answer is just going to be minus 40. Let's go on to the next slide. So here's how you would actually do it, and you should know how to do it. I mean, not that you would want to have to do this on a test, but you just do what I said. You just substitute X for TF, or for C, degree C, you substitute X. Or you can use this formula if you want. It doesn't matter, and then substitute in for X. Either way, you're going to get the same answer. You're going to get X is minus 40. Let's go to the next slide. All right, density, the next topic is mass per volume. So let's say you've got water. Well, water weighs, or has a mass better, of 1 gram. Every time you have 1 milliliter of water, it weighs 1 gram. So if I have 2 milliliters of water, it's going to weigh 2 grams. And actually, we're going to remember that. So that's another thing. You might want to make a little list of these little things that I'm telling you might want to remember, because you really need to. So just to review quickly, Three things right now I can think of off the top of my head. 1 centimeter to the third is the same thing as a cc, is the same thing as a milliliter. And then the temperature at which degrees C equals degrees F is minus 40. And then the density of water, we're going to consider it to be 1 gram per milliliter or 1 gram per cc, with a very, very few exceptions in this class and in 1412. When we do the exceptions, I'll remind you. So density can be listed in any of these. These are all the same. It can be listed in any of these. And the formula for density is mass per volume. So if you had something that weighed, let's say 10 grams, and you had 1 milliliter of it, then it would be a density of 10 grams per cc, or 10 grams per milliliter. If it weighed 20 grams and had a volume of 2 milliliters, you divide 20 by 2 and you get the same thing. You get 10 grams per cc. Next slide. So here, look, before we look at the answer, the mass is 17.8 grams and the volume is 2.35 centimeters to the third. So just divide 17.8 by 2.35 just on your calculator. It looks like you should get about 7 or something like that. And that would be 7, whatever it is, grams per centimeter to the third power. So, and they actually did this. I didn't separate out the answer. So it's actually 7.57 grams per cc. Next slide. What is the mass of a 49 so here, a 49.6 milliliter sample of liquid has a density of 0.85 grams per milliliter. So they are asking this in a different way. So what we have to do here is, instead of using the formula that we just had, which was density is mass per volume, here they're giving us this. They're giving us this, and they're giving us the density. So they're pulling a sneaky one on us here, and they're giving us two things that are not on the same side of this equation and asking us to figure out the thing I just circled, which is the mass. So all you have to do here is rearrange this equation here to get what you want, which is the mass, on one side by itself. And to do that, you just multiply both sides by the volume. So when you multiply this side over here by the volume that you're multiplying it by will cancel with the one in the denominator, these two, and then you'll wind up with a volume on the left times the density. So you wind up with the mass equals the density times the volume. And if you didn't remember this from algebra, when you have an equation, when you have this equal sign, then anything can be done to one side as long as you do it to both sides. You can't just do it to one side. So we can multiply both sides of this by the volume, and then we have it the way we want it, or we prefer it, because now we know the density and we know the volume. Now there's one other thing we need to do, and that's to make sure that we have the density in the right units and the volume in the correct units. So if we want to end up with an answer in grams, which we do, then we will want the density to be in grams per milliliter if we've got a volume in milliliters. So, and it turns out that they actually gave it to us that way in the problem statement, but a lot of the time they won't. So for your class 1311, one of the big things they do that isn't really learning new chemistry is they'll give you the problems, but they'll do it, like, for example, so that you have to do a lot of converting around from one unit to another. So for example, here, they could have given you 0.0, which it just takes forever to write these out, but 0.0496 liters. So part of your problem would be, if this is in liters, how many milliliters is that? Well, so you use your conversion factor. Your conversion factor here is that there are 1,000 milliliters in a liter, right? So if you have 0.0496 liters, then 10, 100,000, move the decimal place, 10, 100,000, 1,000. So move the decimal place 3 places to the right, and that would be 49.6 milliliters, which is what you have here. So it's really a little bit unusual that they would actually give you the units in exactly the form that you need them. So just be warned and be advised of that, that a lot of this class is the annoying thing that they keep doing, where they keep giving you units that they know you don't want them in that units. And the whole point of it is just to give you practice. So don't worry about it too much, but it's just something that you'll just have to live with. So anyway, when we multiply the 49.6 times the 0.85, we get 42 grams, where these 2 milliliters right here and right here cancel each other out. Okay, next slide. All right, so let's run through this next slides fairly quickly. Matter, we're going to do some other definitions. So matter is anything that has mass and occupies space. So that's just a basic high school definition of matter. Anything that has mass, and what we mean by that is anything that's heavier than like a neutrino, or including a neutrino. A neutrino actually has a rest mass. As far as I know, it's the lightest, if you want to look at it that way, particle that we know of. I mean, it has barely a mass, as opposed to something like light, which doesn't have any mass, right? So anything that has mass and occupies space. So does a neutrino have space that it occupies? Yes, it's just not very big. So anyway, that's matter. You probably never will see this again, but nevertheless, there's the definition. And it exists for our purposes in 3 states: solid, liquid, and gas. Solid, liquid, and gas. And you know what these are. There are other phases that matter can exist in, like plasmas, and we'll talk about the supercritical fluid here in Chapter 10. Plasma we don't really talk about in the whole general chemistry course. And then there are other things that people would consider to be different, but don't worry about that for right now. So like if you were dealing with water, water would be a liquid. The solid form of that would be ice, and the gas form of water would be steam. Okay. Anyway, you probably won't ever see most of this again. Let's go on. So here's another picture of it. So when water is a solid, it's ice. When it's a liquid, it's water. And when it's a gas, it's steam. You can see that the density between these two is about the same. Actually, water, we're going to find out in Chapter 10 that water is different from almost everything else, and that when it makes ice, it's actually less dense. And the reason is because of these hydrogen bonds here, which we'll talk about these later too. So, I mean, there are hydrogen bonds that form between water molecules. Don't worry about it right now. We'll talk about it in detail later. And because they form when water is turning into ice, they hold each other in these little like places with air pockets in the middle that are not present in the water. I mean, there's a little bit, but not like the ice. And so the ice is less dense. And I'm getting off on a rabbit trail, so let's go to the next slide. So a substance has distinct properties in a composition that does not vary. And there are 2 types of substances, so I wouldn't worry about trying to remember the name substance, but you should try to remember elements. Elements are made of atoms. And again, I'm going to use this clumsy way of trying to write this stuff. It might be better if I could actually use a mouse. I don't know if it'd be much better, but it might be a little bit better. Atoms and compounds are made of molecules. So like water, like a glass of water. I'm just going to write MC here to save like an hour of time. Okay, so that stands for molecules. So compounds would be like a glass of water is a bunch of molecules. It's not a bunch of atoms. It's molecules that are made up of atoms. So, I mean, it's not confusing. It sounds confusing. It's not. Compounds would be like water. So a glass of water's got a whole bunch of molecules of water. So because it's made up of molecules, we call it a compound. Something that's only made up of atoms is called an element. So as we said before, like copper would be an element. It's like pure copper because all that's in it is atoms. All right, let's go to the next slide. So a solid has these characteristics. It's rigid and it has a fixed volume and shape. So think of a pencil. Okay, a pencil's a solid. It has a fixed volume and a fixed shape. Next slide. Liquids have a fixed volume, but they don't have a fixed shape. So that would be like a glass of water. So the volume is constant, but the shape isn't. So if you take the glass and turn it a little bit to one side, the water will shift its position. Next slide. And then a gas doesn't have either one. It doesn't have either a shape or a volume. So you can actually take a balloon where you've blown it up and tied it up, and you can squeeze it up so that it becomes smaller. You're just making the air particles inside the balloon get closer together. And we'll talk about that in Chapter 10. Next slide. It's about 20% oxygen. Okay, so air is also a mixture, and it's a homogeneous mixture because you can't look at the air and say, oh, there's an oxygen, there's a nitrogen, there's a water, there's a CO2. Okay, next slide. So again, you'll want to try to remember this because it shows up on the final. Elements are pure things that are made out of atoms. So element and atom both start with vowels, E and A. So if you want to remember it that way, you can. And compounds and molecules both start with consonants, M and C. If you want to remember it that way, but you do need to remember that. Okay, so that's one thing you should write down on your piece of paper if you want to. Next slide. Mixtures can be homogeneous or heterogeneous, and we just talked about that. So I'll let you pause here if you want to read the slide. I'm going to go on. So concept check, which of the following is homogeneous? Water, is that? No, that's actually a compound. We've already talked about that about 3 times. Gasoline, I also just talked about. It is a mixture, right? We said it's like hexane, heptane, octane, nonane. There's probably some decane in there. All those are all just carbon compounds that just have varying lengths. A jar of jelly beans is kind of like a homogeneous mixture, right? But not exactly, because you can see, this jelly bean here maybe is a little different from the other one. Soil is also, so a jar of jelly beans and soil are heterogeneous because you can see like the different particles in them. Copper metal is not a mixture at all. It's a bunch of atoms put together, so we call that an element. Okay, so let me just put C here. That's a compound. And then this one right here is an element. And that's not a C. I'm going to make the middle part there. This is a heterogeneous mixture. This one is heterogeneous. So I'm making X here. And this one is heterogeneous. And I mean, I wouldn't spend like 2 hours trying to figure out why these are. And so this is going to be our answer here. Next slide. Okay, so I mean, this one right here, let's put a question mark here because you can make the argument that I think I see the point. I never realized this before. I guess what they're saying is it's not a mixture at all, right? Okay, if you think about it, it's just all the same thing. However, having said that, I don't know, because it isn't an element or a compound. Anyway, let's just go on. Next slide. So the answer is gasoline. Next slide. Okay, and we've talked about this before also. We said when we boil water, it isn't a chemical change. So it's a physical change. You're just changing the state from liquid to gas. So what would be a chemical change? Well, the most obvious and the one that you see the most commonly is if you burn something, that actually is a chemical change, because what you're doing, like if you're burning paper, you're burning mostly carbon and hydrogen that are together in the paper. The paper is made up of littler, smaller things that are made up mostly of carbon and hydrogen. They're called hydrocarbons. So when you burn it, you're burning these hydrocarbons like C6H12 or whatever, or C6H14, that are all tied together in the paper, right? And so what you're doing is you're taking the hydrocarbon and you're adding oxygen to it. When you burn it, oxygen from the air gets in there and gets involved in this. And then you're producing H2O and CO2 gases every time. Every time you burn anything that has CH in it, then that's what you're going to do. You're going to produce carbon dioxide gas and also water vapor. But you'll realize after you look at it for a minute that you've changed the chemical structure, because you started off with carbon that was bonded to H, and you started off with O2, and now you don't have the O2 anymore or the CH. You've now got something different. So you change the internal structure of those things. So that's called a chemical change. Next slide. So a physical change is a change only in the form, but not in its composition. A physical change can also be used in chemistry to do some things like to separate mixtures, and you'll do this in 1111 in your laboratory, or I mean some of them. Like, for example, filtration you will do. You might do chromatography. If you don't do it in 1111, you might do it later in another lab. So filtration just means you're just filtering out something out of a liquid, like particles, for example. Like if you had water and you put just some soil or sand in the water, then you can pour it through a filter paper, right? And the water will go through, but the sand and the soil won't. Uh, if it's soil, a little bit of it might go through, but not all of it. So that's filtration. Chromatography takes advantage of the fact that some things will absorb to certain types of paper more readily than other things. So you can put like a mixture or a solution on a piece of chromatography paper, and you can watch as the different things go up the paper at different speeds, and it will actually separate them out. So you'll start off with a mixture, and then one thing after another will separate out. I've got a picture in here of that. And then distillation you'll do in organic if you take organic, okay? So that's, and also on the ship channel. So that's what they do a lot of on the ship channel, is they start off with crude oil and they distill it into about, gosh, 50 maybe different things. So they do make it into gasoline, but they also make it into a bunch of other stuff like heating oil, kerosene, propane, butane, just on and on. Methane, I mean, they make it into all kinds of things. And the way they do that is by distilling it, and distilling it takes advantage of the fact that different components of the crude oil will boil at different temperatures. So you raise it up to the first boiling point of the first thing and boil it all off. And then once it all has boiled off, you go on and raise the temperature until you get to the boiling point of the second thing, and you boil it all off. Now, it won't be 100% pure, but you can do it again and again until you have it pure. Next slide. So here's a picture of filtration. They started off with this kind of like yellow stuff in this liquid here, and they pour it through the filter paper, and the yellow stuff is all this yucky looking stuff that looks kind of like mustard is all stuck on the filter paper. And now notice here, this one, wow, this one worked really well, because all you have down here in the beaker is water. Next slide. This is the way that you'll do this in organic. So this is a distillation apparatus, which this is actually the best experiment we do at HCC as far as I'm concerned. But anyway, so you start off here with something that's mixed together here, and you distill it, and then you get one of the components, one of the pure components, to come off over here by boiling it. And you just boil this one thing, and everything that doesn't boil at or below that temperature will stay right there. And the thing that you want comes out, it boils, it comes, let me draw this, so it comes up this little tube here, and then it condenses in this area, and then it eventually will cool off and drip down here, and you've got yourself a pure product. Next slide. And then here's the chromatography business, which you may do this at HCC. If you don't do it here, you may do it somewhere else. So you just take a mixture and you stick a piece of this paper in it, this chromatography paper, and different things will go up from the mixture at different distances. Like here, notice here at the end, by the time we get to the end here, or I'm not sure which direction they're going. I guess they're starting at the top on this one. So you start off at the top here, and they separate out slowly. I mean, this whole thing can take hours. But at the end of the day, you wind up with whatever component A is here. B actually traveled farther and C actually traveled even further than B. But the beauty of this is it separates everything out. But the problem is that it's such a tiny amount. But it's something that's good to use like in a police lab or some other kind of a lab where you're just trying to see what's in the mixture. Next slide. So chemical changes change whatever it is that you started with, and this is methane is natural gas. It's CH4. If you burn it, which we've already talked about this, so I'm not going to spend a lot of time on it, you're actually reacting it with oxygen in the air, and you form the same two things every time, CO2 gas and H2O gas, or water vapor, but you're changing the chemical constitution of the methane and the oxygen. So it's a chemical change. Next slide. So which would be a chemical change? And I'll give you a hint. Look for burning. So if they ask you this on a test, or if I ask you this on a test, look for something, first of all, that's burning, because anytime something burns, it's a chemical change. So do we see burning? Yeah, we do. Here it is right here in the second choice. So that's probably going to be our answer. In fact, it is our answer. Dissolving sugar doesn't change the sugar. It just like puts water molecules between the sugar. Melting a popsicle just changes it from a solid to a liquid. Crushing rock salt, it doesn't change it from a solid to anything else. It just makes it smaller, but that's not a chemical change. Next slide. So the answer here, next slide, answer is going to be burning. Always look for burning first. If you don't see burning, then you can worry about whatever other possibilities you have. And then intensive and extensive. Intensive is something that's inherent in that substance. Like, for example, salt has a certain taste, right? And so it doesn't have to be a lot of salt, as you well know, for it to taste like salt. It tastes like salt even if there's just a little bit of it on your eggs or whatever, or your steak. Uh, Color is another example of that. It doesn't matter if I've got uh, one little tiny piece of copper or a whole wire, it still has that copper color. So color, taste, odor, specific gravity, density, um, things like that are considered to be intensive. Extensive properties do depend on how much you have. That would be like the total mass, the total volume. Next. Okay, so look, it's at half an hour. I didn't mean to go this long. This is the first one. So, I mean, I'll probably not talk as much about things that aren't really relevant in the next remaining slideshows. But anyway, or maybe I will. But anyway, I hope you enjoyed this. I hope it was helpful. And we'll see you in the Chapter 1 worked problems.